Hi, my dears. In the last session, we talked about refraction. So, refraction is the phenomena when the light ray, which travels obliquely from one transparent medium to another, will undergo a change in the direction of the propagation of light. And now we'll be going further. We already discussed some phenomena which we see in our day-to-day lives, and now we'll be going into the laws of refraction. Earlier, we learned about the laws of reflection. The first law is quite similar to the laws of reflection. The laws of refraction says the incident ray, the refracted ray, and the normal to the interferes of the two transparent media all lie in the same plane. See here, this is the incident ray and this is the refracted ray. Why refraction? Because it's in the second medium and this medium is a denser medium, so it's moving closer towards the normal. So as it enters the second medium, the speed of light changed, and because there is a change in the direction of the propagation of light, we call this as refraction. So the angle which the refracted ray makes with the normal is called the angle of refraction. See, the incident ray, the refracted ray, and the normal at the point of interference of the two transparent medium. So this is the interference of medium 1 and medium 2. So at this junction, at the point O, what happens? All these lie on the same plane. And the other second law is that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant, which means this angle, the angle I and angle R. And this I and the angle R, the sine of the angle of I to the sine of the angle of R. This ratio will be a constant. And this constant is otherwise known as called as the refractive index. And this is the second law. And the conditions for this sin I and sin R to be a constant is applicable to the light of a given color. So you cannot compare the sin I to sin R of say a white light and a red light. So if you are looking for a light of say white light, your sin I and the sin R should be of the same light. Okay. Well, and also as we said, for refraction to happen, the angle with which the incident ray makes with the normal should be less than 90 degree. So the angle will be the incident angle will be less than 90 degree, should be less than 90 degree, and also it should be for a given pair of media. So the refractive in the sin I to sin R, you should be talking about only one pair of medium. It will be different for a different pair of medium. Why? Because the speed of light will change according to the change in the media. So this law is known as a Snell's law of refraction. So this sin I by sin R, where I is the angle of incidence and R is the angle of refraction, is a constant, is a Snell's law. And this is called the refractive index. And so the refractive index, when we say, we compare it, it is a relative term. That is, we relate it to somebody and then only talk about this refractive index. That is, how do we relate? We relate the refractive index of the second medium with respect to the first medium. So with respect to the first medium, only we'll be discussing about how far it has bent, right? So in refraction, we have simply in simple terms, we defined it as the bending of the light ray. Likewise, refractive index is the extent of the bending of light ray. See, for example, the light ray was expected to travel in a straight line. This is what we expected. But just because the speed of the light changed in the second medium, what happened? And this medium is a denser medium, it bended towards the normal. The extent of this bending is from where we expected this parallel line to a straight line to this extent. So that extent of bending is otherwise known as a refractive index. So that is always in comparison with the the first medium. That's how we compare the refractive index. So the extent of bending is otherwise known as the refractive index. And yeah, So in refraction, we said the light ray will change whenever the refraction happens. It happens only because the light ray will change its direction. Why does it change its direction? Because the speed of the light is different from the first medium and the second medium. So and according to the optical density, when we say rarer medium, we meant to say that it is an optically rarer medium, which means it will allow the optical activity easily. And optically denser medium or simply denser medium, we meant the medium is optically denser, which means it will not allow the light to easily pass through. So the extent of its change in the direction of the path for a given pair of media is expressed as the refractive index. Okay, and refraction, as we said, is because of the speed of light. And well, the speed of light in vacuum. This we have to remember this particular value for the speed of light in vacuum, which is nothing but 3 into 10 raised to 8 meter per second. And the light travels at the fastest rate in vacuum. The speed of light in air is marginally very less. There is no much difference when we compare the speed of light with air and vacuum. So for convenience sake, we take the speed of light in air also as 3 into 10 raised to 8 meter per second. Okay, so the speed of light reduces in an optically denser medium. As we said, when we say denser medium, there are more particles which will decrease the speed of light. So the speed of light will reduce. The value of the refractive index for a given pair of media depends upon the speed of light in those two particular medias. So we can define this by the equation. Why the refractive index is now directly linked to the speed of light in those particular mediums. So the value of the refractive index of these two media is directly depending upon the speed of light. So if we write the refractive index is represented as n and of that particular medium. So this is like n21 means refractive index of the second media with respect to the first media. If you write N12, which means refractive index of the first media with respect to the second media. Okay. If it is N21, that is a refractive index of the second media with respect to the first one, is the ratio of the speed of light in the first media to the speed of light in the second media. So the speed of light in the first media is V1, the velocity of light in the first media. The speed of light in the second media is V2. So the refractive index of medium 2 with respect to medium 1 is the ratio of the speed of light in medium 1 to the speed of light in medium 2. And here, as I said, refractive index is a relative term. Why? Because we are relating it to the other medium. So relative refractive index is nothing but the refractive index of one medium with respect to another medium. And also we have absolute refractive index. Absolute refractive index is otherwise referred as refractive index itself, which means refractive index of one medium, we compare it with the refractive index of the vacuum or air. So as I said, speed of light in air and vacuum is taken as 3 into 10 raised to 8 meter per second, which is otherwise noted by C. Okay, so refractive index, that is n of this particular media, will be the speed of light in air divided upon the speed, the ratio of the speed of light in air upon the speed of light in vacuum. That is, the speed of light in air or vacuum is C. And the speed of light in that particular medium, if we call it as V, then Nm, the refractive index N of that particular medium, Nm, is equal to C by V. This formula we'll have to remember. So refractive index is nothing but the speed of a absolute refractive index of a particular medium. If you're saying it is the speed of light in air or vacuum to the speed of light in the particular medium. So C by V. So the refractive index of water, that is NW, is 1.33, which means what? It is the ratio of the speed of light in air to the speed of light in water. That is the speed of light in air, we know 3 into 10 raised to 8. So then we measure the speed of light in water. And then that ratio is your refractive index of water. So this is the absolute refractive index of water. The optically denser media will not possess it is not always necessary that it should be possessing a great mass density. That is, for example, in your questions. There may be questions that may say light entered into kerosene or light entered into oil, and then what is the refractive index? Then after entering oil, it entered into water. So there is a chance that you may think of it as, where oil will float on water or kerosene will float on water. So its mass density is less. So there is a chance that you may think that it is optically denser. No, it is not. See, the optically denser media, though kerosene and oil is lighter than water, the optical density of water is much less than the optical density of kerosene or oil, which means this kerosene or oil is a highly optically denser medium than water. Okay, so it is not always necessary that an optical denser medium must have to have a greater mass density. Okay, optical density means the ability of the medium to let the light pass through, or it is that property of the medium that will determine the speed of light in that particular medium. So an oil or kerosene will have a higher optical density, or that will reduce the speed of light. The speed of light will get reduced in kerosene or oil than the speed of light in water. So refractive index of kerosene or oil is greater than the refractive index of water. Okay. If in case the optical density of greater means what? The refractive index of the medium is larger. Okay. The refractive index, when the optical density is greater, which means the refractive index is larger, or if the optical density is lower, okay, which means the if it's a denser medium, refractive index is also high, it's a larger value. So the speed of light will be denser medium, speed of light will be less. So when the refractive index is less, which means it's an optically rarer medium, so the speed of light is more or is high. Okay, so I just concluded it like this. The optical density is high means what? The refractive index is also high. Refractive index means what? The extent of bending of the light is more in that case. In that, when the light ray comes more closer to the normal, the speed of light will actually decrease. Okay, when the speed of light will decrease when the light ray moves more closer to the normal, and speed of light ray will increase as the light ray moves away from the normal. That is why the speed of light will be higher when the speed of light will be lower when it is a denser medium, and the speed of and in the denser medium, how it moves more closer to the normal. In the optically rarer medium, the speed of light is faster or is higher, because and the light ray moves away from the normal. And we already explained the phenomena using refraction, that these bending at the junction of the pencil. See, the light ray, it entered into a denser medium, so it moved more closer to the normal, and so the speed of light reduced in this particular medium. So denser medium, so then optically denser medium, refractive index is higher, speed of light is less. This speed of light is less, so we tend to see the light of the light coming from a different direction, and you see the pencil has broken, or all these illusions are because of the refractive pattern of light as it enters from one transparent medium to another and enters a transparent medium in an oblique way. That is, the light enters a transparent medium in an falls on the second medium in an oblique way, and also and this refractive index, when we talk about it, or the sign of the angle, that is the refractive index. If we talk about, we are talking about one refractive index for a pair of media. It's a relative term. We represent the bending of the light ray for a particular color, the light of a definitive color, and for a definitive pair of media. Okay, so thank you, dears, for your attention. And we will continue with the index questions in the next session. Thank you.